I love three things: solving difficult problems, my cat Newton, and competitive esports.
Hello.
One enemy remaining.
He's one. 148.
These games require their players to quickly and precisely move their mouse to a target and click. In recent years, programs such as Aim Labs have become popular because they allow players to hone the skill in a low-stress environment. One day, I was scrolling YouTube when I saw a video from Kamal Carter about a mouse connected to omnidirectional wheels that could aim much better than the average human. Feeling inspired, I decided to make my own aiming robot. Over the next 3 months, this side project became a journey in mechanical design, computer vision, and electronics, teaching me skills I'm excited to bring to real-world engineering challenges. The first challenge was designing a mechanical system that improved on Kamal's robot. His design relied on a mouse with an older sensor and heavy moving parts. I realized I could boost accuracy and speed by using a gaming mouse with a high pulling rate for better precision, reducing the moving mass to increase acceleration, and mounting the mouse to stationary actuators for stability. I decided to stick to a simple 2 degree of freedom Cartesian style robot driven with 2 of the cheapest servo motors I could find. These servos are used for model airplanes and low torque applications, so they'll do just fine for my project. After designing and printing anchors that could stay in place on my desk and hold servos, I needed a way to connect the mouse to the linear motion provided by the servos. Thankfully, Logitech has a 3D model of the mouse on their website, so after a little inspection magic, I had a perfect reference to make a physical mouse container, and I came up with something pretty nifty. Because of this mouse's design, it was possible to have 2 anchor points in a 2-piece system that could easily be put on and taken off with 2 screws. Now that the mechanical part of the project is complete, I need to move on to the software. As Sun Tzu said, in order to click a ball, one must first identify a ball. With this ancient wisdom in mind, I harnessed the power of machine learning by following a YouTube series from Learn Code by Gaming. This series taught me how to use screenshots of targets on the screen to train a computer to recognize them automatically. While this method worked some of the time, it was unreliable, and I opted for a simpler solution using OpenCV, an open source library for Python computer vision. After taking a fresh screenshot from the Aim Labs window, I applied a color mask over the image and used OpenCV's tools to identify which of the remaining blobs had enough area to be considered a valid target. After identifying all of the blobs of pixels as balls, I found the centroid of each ball and calculated which one was the closest to the center of my screen and the X and Y distance in pixels to get from my crosshair to that centroid. I converted the distance from the center of the screen to the center of the ball, changing it from pixels to angles that the servos could understand, and then sent that data over. I implemented a PID controller system to better control the accuracy and smoothness of the servo movements without over or undershooting the target. Now that the mechanical systems and software programs were set up, I wanted to make the electronics more interesting by adding a solenoid that would physically click the mouse button. I made a circuit that featured 2 NPN transistors to invert the Arduino signal and a power MOSFET to release additional power from an external power supply to the solenoid when the Arduino told it to. I first modeled the circuit in Tinkercad for the pre-built Arduino implementation, and then every circuit for the more in-depth analysis before building it, and after hours of reprint and troubleshooting code, it worked. Now this system isn't perfect. Sometimes one servo will refuse to go to the location the Arduino tells it to. It's not as fast as Kamal's robot. There is much to be desired with a PID controller tuning, and only one servo begins its motion at a time, but it does its job valiantly. If I could do this project over, I'd get better actuators for quicker motion, optimize the code to minimize redundant calculations, and continue to tune the PID controller. This project challenged me to integrate mechanical design, microcontroller communication, and electrical systems into a cohesive solution. It reinforced the idea of iteration. Every obstacle, from mechanical design to software debugging, was an opportunity to learn and improve. Thank you for watching, and let me know what I should build next.